All right, let's start. So do you have any questions from homework 2? Nothing? Okay, shoot. Yeah.
So, like, I'm really like trying to think of this in terms of like x and y because they're only using two axes. We're not worrying about the x-axis shift, but worrying about y, z. So I'm thinking that it's like the same as iy, really, right? So that would be the double integral of y squared dz dy.
Oh, okay.
Coming into y squared f of y dy and all that stuff, right?
Okay.
So for the y squared, would that just be like, would that turn into like the height cubed? So then it'd be 1/3 times the Simpson rule plus 2/3 times the Simpson rule? Or would it be like 1 squared? Like, I don't really know where those y squareds come from.
Okay, so let's see. First, what does it say? Determine one moment z-axis. Okay, so let me switch this.
Professor, what was the question? It was kind of hard to hear that.
Okay, yeah, so he asked about question 1, part 5. Compute the area moment of inertia about the z-axis. So before we do that, let's look at number 4, which says determine the 1D integral for doing the same thing, for computing the area moment of inertia. So 1,4, basically, if you want area moment of inertia about this axis, this is the z-axis. What do you think of? So you think of the whole hull rotating about this axis. Okay. So the iz, the full integral, the general form would be this y squared dA. And this is what you were saying. You were saying, all right, we put down the limits. Let's say z goes from keel, let's call this 0, all the way up to the waterline. Oh, this is given as waterline 5?
Yeah.
Okay, so waterline 5 is what I will write. And then y goes from, look at this. You have to go from negative f of what? What is this? Yeah, see, this depends on the z value. So this distance from the center line becomes a function of z. And the other guy is a positive f of z. So negative f of z to positive f of z, y squared dy dz. And when you do all of this, you get basically, what do you get? 1/3? 2/3, yeah, 2/3, 0 to waterline 5, f cube z dz. Yeah, so this is what you were saying, all right? Yeah, this is not, the x-axis is out of the picture here because we're only working with one x location.
Yeah, see, I was thinking it was going to be like y squared f of
Y squared times f of, y squared is f squared.
I think I was doing dz dy. Yeah, I was doing dz dy.
Oh, no, see, y, no, you have to integrate in y first because That limit depends on the z value. So that is same as what we did for the x. Now we do it using z. All right. And once you have this, then the next question you had was, how do you use Simpson's rule for this?
Yeah, just trying to like figure out where the
All right. Would you be able to do Simpson's rule on this now?
Yeah.
Okay. Yeah, it's very almost identical to the IIX that we did.
Excuse me, what do you mean by waterline 5?
So
waterline 4.
waterline 4. Okay. So that's the design waterline that's given. So we basically have to start at the keel and go all the way to the waterline. And I assume this is the 4th point given to you?
Right below, it's right below number 5. It says waterline.
Oh, okay, okay. So we go to waterline 4. Yeah, because we don't care about what's above water. Oh, sorry, this is also 4. All right. Let me switch back to the homework. All right, more questions?
I'm still confused on that. In problem 1, we have BL, and then we have 1, 2, 3, 4, 5, 6, 7 values going to DWL, and I assume BL was at the keel and DWL was at the waterline. Am I wrong on that?
BL is you're correct, that's the keel. DWL is the design waterline.
Okay, then I still go back to what do you mean by what you just said here about WL5 or 4?
That's this part. Assume that the ship floats at waterline 4. You don't necessarily have.
Okay, all right.
Yeah, so at that particular instance, the ship is floating at waterline 4.
All right, so that would be 0.4 there that's on there.
Correct. And this guy.
Okay, got it. Okay, sorry.
Okay, more questions? All right, anything on problem 2?
For question 1 of problem 2.
Question 1 or problem 2, okay? What is?
To find the displacement, you have to use delta equals rho g nabla, right?
Yeah, that's.
And then in salt water.
Yeah, so rho of salt water, G is constant. Nabla is what you need to find using integration. Yeah. Okay. All right. Nothing else?
I mean, I'm still confused on problem 2, like number 2 a little bit, but
You say problem 2, number 2?
yeah, right. Yeah, right. I know it's like the summation of them, but of the
Right. So let's see. Let me switch again. So crap. Okay, let me. It says appendage, blah blah blah. All right, all right. So basically, what it is saying is, you have your hull and you attach something on the bottom. Okay, some solid object. So think of what you have done. What happens to your what happens to the displacement?
it gets larger.
Okay, so yes.
Well, doesn't it depend on whether the appendage has got a density greater or less than the water?
Correct, correct. Yeah. So see, there's several things happening. You have added a mass to your boat, and you've changed the submerged volume by adding this thing. Okay, so let me read the problem. Assume that there's an appendage. Volume is given for this guy. So you're given, let's call this V2 is given. It's 200 whatever meter cubed. Centroid of volume 1 meter below the BL. Okay, so we're below the keel. Okay, so we're told that this thing has a centroid that's, what is it, 1.1 meter. Volume is what, 262 meter cubed. All right, and the question is, what is the delta displacement and what is the KB? What is the KB with the thing attached? Okay, so well, I should have told you that the submerged volume of the hull doesn't change. Because I think I missed that in the question. So you were talking about density of this guy. So it depends on the density of the additional object, whether your hull will sink further or start floating up. Or rise up in the water. If it's a block of wood, you'll rise up a bit because this thing will provide extra buoyancy. If it's a block of steel, your hull will sink further down. Okay, so assume this density is equal to density of salt water. In that case, there's no change in buoyant force. Okay. Well, no, don't assume that. It becomes complicated. So add this to the question. Assume the water line does not change after adding the object, after adding the appendage.
So does that mean the submerged volume we saw for in 121, like right before it, is the same?
The submerged volume remains the same. Yeah, if the water line does not change, the submerged volume is what we've already computed earlier.
Since we already have that from the before.
Okay, let me see. Where did we compute this in question 1?
Yeah, because you needed it to get a Z-bar or BKB.
Okay, all right, perfect. So we already have that from before, and so let's see. The main thing is how to compute the new center of volume. All right, so let me redraw this guy. Let's say the initial center of volume was here. E0, so this is KB0. And this new guy we've added has another here, B1. This is KB1. All right, and then we're asked, how do you compute KB combined? All right, so the only thing you have to recall here is how we compute, if these were two-dimensional objects, how would we compute the combined center of the centroid area, right? The area centroid. If you look back to your notes, we did this. If you have one object here and you add another object here, the XC combined is basically X1, A1 plus X2, A2. over A1 plus A2. Okay, same for center of mass. Instead of area, you put down mass. Exact same thing we do here. We'd say, all right, this is KB0 times nabla 0 plus KB1 times nabla 1 over. Okay. So you've already computed however many meters it may be, and this the new thing is given to us as 1.1. There's just one thing you have to be careful of. Should I put a plus or a minus here?
Minus because it's going below it, right?
Correct. So this key line.
Below 0 anyway.
Yeah, the key line is my 0 line. So this is z equals 0. So since we add this at z equal negative 1.1, that value would be negative. Yeah, that's this. Correct. To find the total displacement, you add, well, you have the total volume and times rho times g. Okay, let me see if that was all for that question. What is displacement, delta, and centroid? Yeah, okay, that was all of them. Okay, any other questions?
John, I just want to double check for problem number 1 to the centroid, I want to double check the formula.
For problem number 1,
Centroid of midship section ZB.
centroid, okay.
I just wanted to make sure I had the right formula. I gotta find it now.
So let me just, part 2 is, what does it say? Centroid of midship section. And ZB. So let's draw a sketch. The front view, this is our midship section, waterline, center line. Okay, centroid of midship. So we're basically asking, starting from, if this is the keel, where is the centroid located?
Somewhere on the z-axis.
Yeah, on the z-axis. So it will be on the z-axis. We need to find out this distance, basically. All right. So how did you start?
How did I start? Well, I was looking at the formula 1/2 f squared of y dx, which would be f squared of y over my gx over the integral of f of y dy.
All right, all right. So see, the formula you're talking about is already simplified. It's always better to start with the general formula. I think you'll end up with the same thing, but always better to start with the, at any location z, we got an element dA. This is negative f of z. This is positive f of z. And for centroid, we have zb as double integral of z dA over double integral of dA. All right. So see, no matter what the geometry looks like, we always start here, put in the limits, and we'll get the correct simplified version. So what do you say the limit should be in this case?
Negative f of z to f of z.
All right, negative f of z to f of z. That's the y.
Oh, that's the inner one, yeah.
All right, and
the outer should be what, 0 to what's the top, the DWL or the water line?
yeah, the water line. Okay, and we have z dy dz. over area. That guy is just area. All right, and then when you simplify this, it becomes 0 to waterline z f of 2 times f of z dz over area. Yeah, this is just constant dy becomes y, and f minus f gives us 2f.
Don't you need to put your dz before the dy?
Because you, I wanted to integrate in y first. So I've only integrated in y, not in z. But you're basically saying I should swap the dy and dz, correct?
Yes.
Yeah, you can do that. It doesn't matter as long as you explicitly specify that the limits are z equals 0 to whatever. If I don't tell you z and y, then yeah, then it becomes confusing. But if you have those, who cares?
So it's z times.
Yeah, because this is the integral. This is y negative f to f. That's what gives us this part.
So that basically means like, if you're writing it out, it would be like 1 squared over 3 times 8
Wait, slow down. So 1 squared, where does the 1 squared?
The 1 would be like the height. No. All right, so it would be, where would that z? What would that z?
Oh, so you're given at different z locations.
Just do 0, 1, 2, 4, 6.
So you're told the bottom is 0, and what's the first level you're given? 1 meter, 1 feet? Okay, 1, and then 2, yeah, 4. Yeah, so that's basically the z values you put in here. Okay. When you write the numerical integral. I mean, here you don't put in anything. Make sense? Perfect. I mean, any doubts? Okay. Anybody else? Any doubts here? Who asked the question? Chad, is this okay?
Yeah, for the most part, I'm gonna have to go through and just redo the calculations, but that's,
All right, so let me just, because there's only 3 things here, so it'll be easy for me to spot. Is the first guy okay?
yes.
All right, and expanding this into the second guy is okay?
Yeah, that's not bad.
I jumped a bit here, so let me write out one more step. So this becomes z equals 0 to waterline. Take z outside, do the integral in y. Okay, and then is that better?
Oh, okay, yeah, you just broke it down to how you went to the final step to get,
Yeah, and this from here you just get that guy.
yeah.
It's supposed to be f of z, right? Not f of x.
Oh yeah, sorry. Okay. Yeah, I mean, see, it's not very, it's all very simple going from one step to the other. Make sure you understand this and everything else is easy. And everybody knows how to convert this, how to do Simpson's rule for this, how to do trapezoidal rule for this. Yes?
You just say that that's like g of
Yeah,
z.
exactly. This, you say this is g of z, and then just use your Simpson's rule or trapezoidal rule, midpoint rule, whatever. Okay, more questions?
Do we have to make a assumption, or should we know some standard value for the density of salt water?
I will give you all the numbers you need, and if something's not given, just ask me. Density of salt water, it's a bit higher than 1,000 kg per meter cube. Just take it to be 1,000 kg per meter cube. Yeah. Yeah, see, the exact numbers don't matter as much as you being able to set up things correctly and following the steps correctly. Anything else? Okay, any questions about quiz? Remember, next class we'll have quiz at the beginning of class.
What's going to be the format of the quiz? How's that going to work?
Format? Can you? Not sure what you're asking.
Well, it looks like it's timed, like it's available like at 9:30, and then
Oh, okay.
you have to have it submitted by, is it 10:15?
All right, so the quiz will be live just like we are right now. You will have to have your webcam open. Whoever's logged in, I will email you the quiz. Whoever's not logged in does not get the quiz. And ignore the closing time, because sometimes I give you extra time, like 5 minutes extra or something. So I will adjust the closing time and I'll ask you to scan it and post it just like you post your homework. And then we'll have regular lecture.
Okay, because the scanning and the posting, sometimes that takes a little time, you know.
Yeah. So once I say stop, you have 5 minutes to scan and upload. That's your time. It's open book, open notes. You have to have your webcam on. You're welcome to take it in class. I'll bring hard copies here. Your choice. And yeah, that's most of it. Any other questions?
If we have to have our webcam on, does that mean you're going to use that Respondus stuff?
No. Like you are online right now, you just turn on your webcam and we'll be able to see you. Wait, can you see this participant list?
Yeah, okay, so we just, I just turn on the start video.
Yeah, and it'll just be
Okay.
like a Zoom meeting.
Because otherwise the Respondus thing, it locks down your computer, and most of my notes and things are on the computer, you know.
Yeah, we tried that last term. It worked sometimes and it didn't work most of the time. So we will just do it live. Okay, anything else? All right, so let's keep going with.
A question on the chat.
Oh, yeah, I don't see the chat. So are we allowed to use notes on a tablet or computer? Or do they need to be printed? Yeah, that's not easy to answer because you're looking at your tablet. I don't know what you're looking at. Yeah, difficult. Wait, thinking. No, don't use your tablet or another computer. Print out stuff you need to use or write down stuff you need to use. Yeah, that's. Do all of you write on the computer? Man, times have changed.
Yeah, all my notes are online, like in Word documents and stuff.
Okay, how about this? I don't want you to, yeah, some people might not have access to printers, so use your notes, but to compensate, I'll have to make the quiz slightly more difficult, so people don't have time to Google stuff. Yeah, so no need to print. You can use your notes on your tablet. More questions? Yeah, see, I'm old school. I still write on paper. All right, old school. I graduated, what, 10 years ago, so now I'm old school. Funny. All right. Okay, so let's go back to talking about stability. Okay. Just to recap, we had talked about this very simplistic scenario where we have stable equilibrium, unstable equilibrium, and neutral equilibrium. And the same thing with hulls. Depending on how we design it, we either make sure our hull is stable, or unfortunate incidents, it can go unstable. Neutral is a bad situation to be in, because if something tilts you over, you remain tilted. All right, and then we started talking about, okay, when the hull is submerged in water, there's the force due to pressure all around on the hull. And the net effect of this is a buoyant force acting upward, FB. And of course, we have the weight of the hull plus any cargo acting downward. That's what we call the displacement. If everything is in equilibrium, FB is exactly, oh, before that. Don't ever copy paste from anywhere, from Wikipedia, from other people. I saw that happen in homework. Just please don't do it. It's not worth it. You know what happens if you get reported to the dean's office? What? In the last year, you have 2 or 3 months to go and you do this. What happens if this goes up? You fail the class, you have to repeat the class, and the class is only offered next year, spring. I don't care, you have to graduate, you have to start a job. I have no sympathy for dishonesty at all. So don't do this. And you get a lifetime annotation on your transcript about the incident. So don't do it. Okay. All right. So yeah, when everything is in equilibrium, that means the net sum of the forces is 0. Net sum of moments is 0. And then we started talking about initial stability and the metacenter. Okay. And we had just started looking at those things for a hull. Okay. Keel, center of buoyancy is B. G is center of mass or center of gravity. And M is the metacenter. All right. At the moment, we don't know where this metacenter location is, how far away this might be from the keel. But we'll compute, we'll see how to compute that distance. And we said, all right, we have the upright hull, let's tilt it a little bit. And that's the sketch we drew here. By definition, the metacenter is the intersection of the line perpendicular to the water line and the center line. That's the black line, is the center line, right? And it lies exactly above the center of buoyancy at all times. So when we tilt the hull, what happens is see here, the dry volume on the left half was some value, and now it's slightly larger. And the opposite happens on the other side. Now you've submerged some of the dry volume. So the center of buoyancy naturally moves a bit to the right side. Okay. And we'll figure out how much it moves and what happens. Oh no. Okay. Okay, so a few notes. By definition, the metacenter lies directly above the center of buoyancy P, or B prime in this case. This B is no longer the center of buoyancy. B prime is the center of buoyancy. All right. A few more observations. When we tilt the hull, the center of gravity does not move. The cargo on the ship is completely secure, so it doesn't shift. So G remains in place. So location of G does not change if onboard weights are not allowed to move. All right. The thing that does move is the center of buoyancy. Okay. So B does move. Since the new submerged volume has a different center of volume. Compared to the original. All right, and terms that we will use over and over again. This KB, this is KG, AM, did I write somewhere? This is the metacenter. So this is the metacenter. All right. Now, another thing to keep in mind is, if a ship is rolling, unless it's very rough seas, the roll is very gentle. Okay, you almost never go above, let's say, 10 degrees. So in that scenario, what happens is the distance between M and keel does not change as this very gentle roll happens. Okay, it'll of course shift a bit, but the total distance will remain more or less the same. So let's write that down. For small deflection angles, let's say less than 10 degrees, the metacenter does not move a lot. We can consider it to be fixed. Okay, only for small angles. If the deflection is large, so you have a huge roll angle, this, of course, we already know the B center of buoyancy moves sideways. It does so even with small angle change. But the metacenter will also start moving. So the location we cannot assume to be constant anymore. For larger deflections, both metacenter and center of buoyancy follow curved paths. And we'll learn how to use charts to determine this for large deflections. Later. Okay. So it seems metacenter is an important one since we're talking so much about it. To compute the location, we do the following. So we can compute the metacenter location. Okay. So metacenter location, most useful is, well, not most useful. Km is one thing that we use very often. Keel to metacenter distance. And let's look at this sketch. You see, keel to metacenter is basically if we know the Kb distance and if we know the Bm distance, we just add the two. Kb, you already know how to compute. That's the centroid, the volume centroid. Okay, that's what you've been doing for homework 1 and 2. Bm, we have a very simple formula for computing Bm. Okay. So Km is Kb plus Bm. This is centroid of, this is the volume centroid, this centroid of displaced volume. Bm, you compute using I over nabla. Okay, and I'll show you why this Bm is I over nabla. I in this case is our area moment of inertia. And nabla, of course, is the displaced volume. Okay, and that's what we've been learning, how to compute I, how to compute nabla. All right, so we can basically use the knowledge we have to do all of this. Fine, that gives us one of the possible distances, Km. Another important distance in this picture is Gm. Okay? Gm is called the metacentric height. And it turns out that when Gm is positive, your hull is stable. If Gm is negative, meaning if m goes below G here, your hull will immediately tip over. Okay, it'll be an unstable equilibrium. Even a very slight disturbance will make it roll over. So it's very important whenever you design a hull to keep Gm positive at least, and larger if you want to keep a very stable hull. Of course, there's always pros and cons anytime you decide to make it too stable, and we'll talk about that in a second. So also, Bm is equal to Bg plus Gm, which gives us GM is GM minus BG. Okay. So let me go back to the sketch. So keel, KM, keel to metacenter is one distance we talked about. Center of buoyancy to metacenter is BM. Okay. And you see here BM is equal to BG plus GM. That's basically what I wrote in bottom here. BM is BG plus GM. And this gives us a way to compute the GM, which we want. All right, so GM is used as a quantitative measure of initial stability of a floating body. All right, up until now, we've just been saying, all right, we want our hull to be stable. The GM lets us quantify that. Like, how stable is it? Is it a little stable? Is it very, very stable? So, high GM value, large initial stability. Against overturning. All right. Negative GM, unstable. Okay, now imagine you are in charge of designing a new ship. What do you want? Do you want GM to be like very, very, very high? Why do you not want it to be very, very, very high? Say what? So
It's more susceptible to roll.
it's more susceptible to roll?
It's very
Other way around. So large initial stability is,
Oh, so it's not, yeah, okay.
yeah. So large initial stability means something tries to push you over. So something rotates you a bit, you immediately want to come back. Okay. So you're correct in saying you don't want to make it very, very, very large. Why? Yeah, it becomes very sort of stiff to rolling. So it doesn't move at all. Okay. So then structural hull structure becomes an issue because the waves are basically hitting against a solid block that's not moving at all. What happens if you go the other way? If you make GM very small, think about the passengers on the boat. Even a little bit of hull, even a little bit of wave disturbance will cause your hull to do a lot of roll.
We're gonna get seasick.
Yeah, you get seasick, okay? So the passengers on board would not be happy.
The cruise ship would most likely have a higher than like a frigate.
Yeah, so a cruise ship, you should have a higher GM than something you need to be agile. So think about the shape of a cruise ship versus a cargo ship. Cargo ship has a very, very large GM, okay? The reason is you want all your containers that are stacked on top to be very stable. You don't care that the waves are hitting you. So, and the way the hull is designed influences that. We'll see exactly how. All right, and think about canoe. High GM or low GM or negative GM? Yeah, with a canoe, you're almost negative. You're positive, but you know, you're close to zero. So think about what happens when you stand up in a canoe. You basically go face down in the water if you try to stand up in a canoe. And that's because you make the GM negative. Okay, let me bring back the picture. Where is the picture? Okay, look. Okay, look here. G is here. While you're sitting in the canoe, when you stand up, what happens to this G? Just think intuitively. You're sitting in the canoe, the center of gravity is here. When you stand up straight up, what happens to the center of gravity? You're saying the center of gravity goes lower? You have nothing to do. Yeah, it goes higher. You have nothing to do with buoyancy because you are sitting in the dry part. So whether you're standing or sitting has no influence on the submerged volume. The weight has not changed. Just the distribution of weight has changed. You've basically taken your torso from down here up there. So the combined CG is somewhere over there now. And as soon as this G passes the metacenter, you will flip over. Okay. So we will do all of that. Well, at least mathematically. Okay. All right, so one more note here. GM also influences the rolling period of the hull. You can almost think of it as okay. This is just a very crude analogy. Spring stiffness that opposes rolling. If you have a low GM, the roll goes on forever. So it's a very slow roll, but undamped. If you have a high GM, you get a very short rolling period because you get back to being straight almost immediately. Okay. So that's also bad because if you have a very high GM, a slight disturbance makes you want to come back almost immediately. Also not good for passenger comfort. It's a jerky motion. Okay. So as engineers, your job is to shoot for the middle. That's basically what car designers do. The suspension has to be tuned to be not too stiff and not too pliant. Pliant? Pliable? Soft. Okay. So let's see. High GM. Shorter rolling period. And this is good for stability. But again, bad for passenger comfort. Jerky motion. Okay. All right. Now, okay, let's look at the formula a bit more closely. So recall that Bm is equal to I over nabla. That's what we wrote on the previous page. I haven't showed you why, but let's assume that's true for the moment. And we also know this is equal to Bg plus Gm. And let's think about what happens when each of these terms changes. What happens to the Gm, okay? If you design a hull that's narrow and you come to me and I tell you, no, make it wider, what will be the impact on nabla? I don't ask you to change the loading condition, the weight of the thing, anything. I just say, no, change your geometry to make the hull wider. What influence does it have on nabla? You say nabla will increase? Okay, any other? Will nabla increase or not when I just change the hull to be wider?
Will increase.
You also say increase? Okay, now tell me, why will it increase? What does nabla depend on? Volume, all right, submerged volume. And submerged volume is determined by what? No, not area times height. Think about a floating object. Submerged volume depends on, okay, wait, all right, so waterline, but not knowing the geometry of the ship, can you, if I don't tell you the geometry of the ship and ask you how much volume of water is it displacing, what is the one number you need? The weight, yeah? So the weight determines the submerged volume, nothing else. Not the geometry, not the distribution. If I make you widen your hull, it has no influence on nabla, okay? Is that okay, everybody? Very basic concept. So if that's not okay, don't make me go forward, because yeah. The submerged volume only depends on the weight of the floating object, nothing else. That's the main principle of buoyancy, okay? So wide hull means we have no change to nabla since weight unchanged. All right, let's think about the other guy. What happens to I? So let's see a narrow hull versus a wide hull. What happens to I?
It increases?
You say it increases?
Yeah.
Do you have an intuitive explanation for that? What I increases, you're correct, but intuitively, do you see why I increases?
Has a bigger area.
Yeah, so not just a bigger area, it's the distribution of area that matters. So I could have cut this in half and said, all right, I'll make my hull catamaran. Okay, so you see now there's no There's no change in area going from this sleek hull to the catamaran, but the distribution has changed. Okay. Oh yeah, well, not a wide hull, but yeah, okay, okay. But you get my point. So no change to nabla, but I increases. Area distribution. Farther away from axis. Okay, you're just distributing the area farther away from the axis. So I increases. All right. So a wider hull leads to higher value of BM and consequently higher value of GM. And remember, whenever we talk about hulls, initial stability is one term. It means stability to rolling in the neighborhood of your stable configuration, of your initial configuration. Okay. So wider hulls have larger initial stability also. Narrow hulls, let's say narrow boats with twin hulls, have high initial stability. And the reason is what we just mentioned. So since high I, because area spread out farther or distributed farther from the axis. All right. So that's one solution to making your hull stable. You go back and rebuild the hull, okay? If you don't have the choice of rebuilding the hull, what would you do? How would you make it more stable? So
Add ballast.
add ballast, yeah. So you either rearrange your cargo, so you move the G down. Remember, when you stand up in the canoe, you become unstable. If you, let's say, put all your heavy weight down here, you're basically moving the G downward. So you're increasing the GM distance. You're becoming more stable. So that's another easy way to do this. Oh, by the way, you know, when you've seen cranes on cargo ships, when they lift up the heavy containers from the hold, you have to be very careful about not letting GM go negative. And we'll see how all of that happens. With the suspended weight, your GM can go negative. All right, so another way to increase GM. Lowering the location of G. G. Moving heavy containers. Into the hold by sitting low in a canoe. By sitting low in a canoe. So that's the two main ways you can influence the stability of a hull. All right. So we still don't know why exactly a negative GM causes our hull to be unstable. So we'll draw a few sketches and it'll become obvious. Let's draw the first sketch. Okay, we'll work with slightly tilted hulls. So slightly tilted here. Keel, center of buoyancy, center of gravity. Metacenter. All right, and we know when we drop a vertical line from here is where our new center of buoyancy, B prime, will be located. All right, now, so draw that sketch and then I'll ask you one question. All right, now think about this. What are the two forces acting on the submerged hull?
Weight and gravity.
Weight and gravity. weight, gravity, well, that's one force, correct? What's the
Weight
other?
and buoyant force.
Yeah, so that weight or gravitational force is one and the buoyant force is the other. Where do these two forces act? What points?
The buoyant force acts at B prime and the weight acts at G.
All right, so the weight by definition has to act at the center of gravity, G. So we have the gravitational force acting straight down here. And we know this gravitational force, it will be equal to delta. All right, and then the next one is buoyant force will be acting straight up here. Let's call this F buoyant. Do you see a couple happening here, a torque? You see the hull will try to restore itself, okay? And that's our torque arm here. Let's call this point Z. All right, so when this tilted hull is in equilibrium, this tells us a few things. So static equilibrium tells us first thing we know is F buoyant has to be equal to weight. So it has to be equal to displacement. Rho G nabla. And also we know the restoring torque acting on this hull is basically the force times the moment arm. So restoring torque is equal to or you can just as well, right? GZ times delta. Okay, so force times moment arm gives us the restoring torque. Now, to find out what this GZ value, we know what delta is. That's the weight of the ship. To find what the GZ value is, let's do a bit of trigonometry. So let's call this a roll angle be phi. This angle is phi from the vertical. All right, so we know this angle is also phi. And knowing that, we can say this is equal to GM times sine phi times delta. So that's the restoring torque that we get. As long as GM is positive, we get a positive restoring torque. If GM is negative, we get it the other way. That's not a restoring torque. That's actually the torque that will flip you over. And one more thing to remember here is for small angles, for small roll angles, sine phi is nearly equal to phi in radians. Okay, so this is nearly equal to GM times phi in radians times delta. Is this okay? Make sense? So this is, I mean, if you understand this, basically all of stability is in here. We just keep building up using simple concepts on this basic stuff. All right, so this is for GM greater than 0. Let's just draw sketches of what happens when GM is less than 0 and when GM is equal to 0. So for GM less than 0, we've said already that the hull will be unstable, but let's look at the force diagram and see how exactly it's unstable. So quickly drawing the same thing, but not in as much detail. All right, so same as before, center of gravity is where our weight will act downward. Where is the center of buoyancy located? So remember, B was our original center of buoyancy. Where is the new center of buoyancy located? Remember the property of this metacenter? This metacenter is at the intersection of the center line and this vertical, well, the perpendicular to the water line. So our new B prime is located somewhere here. Okay. Where does buoyant force act? So we've already dealt with one of them, the weight. Where does buoyant force act? Does it act on B?
On B prime?
Yeah, that's our new center of buoyancy. So the buoyant force has to act here. So this is FB prime. And you see now that the resulting torque has an unstable influence on the hull. It'll basically tip it over even farther. So this is why this configuration is absolutely to be avoided. The resulting torque from even a small tilt makes the hull tip over even farther. And if that happens, your hull will capsize. Okay, and we're out of time, so we'll draw the other sketch next class. Any questions about this or quiz? All right, study well, and good luck. Okay, see you guys.
Professor?
Yeah.
So is the quiz just mainly focused on the homework assignments we did? Or?
Yeah, if you understand how to do the homework 1 and 2, you're fine.
All right, cool.
Yeah.
Have a good day.
Sure, and it's open notes, so everything's available to you.
All right, thank you.